Today I'd like to talk about the system of simple pendulum where a mass m is hanging from a point via an inextensible massless string of length L. Presumably it can swing smoothly without friction, and the question is why do we need to understand the concept or the system of simple pendulum in order to understand simple harmonic motion? And the answer is quite the other way around. The simple pendulum is a complex system which have a non-simple answer, but under certain condition its motion reduces to that of simple harmonic motion. And it's important to go through this system because it serves us in two ways. Number one, of course, the first one would be under certain condition we can observe the phenomenon of simple harmonic oscillation or simple harmonic motion even in this system, which is the simple pendulum. But also there is another reason, which is which has to do with using terminologies which may be confusing to a lot of students, especially the beginners, because unfortunately we have to use a lot of the terms in different contexts, but we sometimes run out of symbols. And sometimes it's even more confusing because those symbols might be related, but they are completely disparate topics. That means they are fundamentally different objects. And doing this example, going through the motion of this system, will clarify a lot of the confusions for us. There are a couple of ways to find out the equation of motion. The equation of motion relevant to the simple pendulum, and that is what we're going to do. We'll be finding out the easiest one, and that is by utilizing the idea of rotational motion in this context. So notice that this is the system where the mass is hanging from this point O. There is the string of length L, and there is this mass. The mass is placed in a field of gravity, so there is gravitational acceleration. That means weight force has been acting on it, and there is another force exerted by the string itself, and that force is the tension T. Now, the easiest route to find out the equation of motion is, there are actually a couple of ways to find out the same result, but the easiest one by far would be to use the concept of rotational motion. And as we know, the rotational motion has something to do with the analog of Newton's equation, but instead of force we use torque, instead of displacement we use angular displacement, instead of velocity we use angular velocity, and instead of acceleration we use angular acceleration. So that is what we are going to do here. So to find out the torque on the system, we first notice that this angle here is also theta. And if we are willing to find out the amount of torque exerted on the system with respect to this point, by the way, the point from which the mass is hanging, O, in our diagram, let the torque be tau. So tau is equal to the moment of inertia times alpha, where in this case alpha is just theta double dot, which is basically the double time derivative of theta. So theta differentiated with respect to time. Now, the moment of inertia for the system is simple. It's I equal to m times L squared, right? M times L squared. So that would be the mass distribution of the system, and this is the moment of inertia. So that's the torque. So if we substitute it here, we get ml squared theta double dot. On the other hand, if we find out the torque by this formula here, which is r cross f, which is a vector, by the way, tau itself is the vector, and here it is the magnitude of the vector. And after we find out the vector expression here, we'll be taking the magnitude and we'll be equating that. Apart from that, we can see that r is here is given by a vector which directs in this direction. So let this be our x direction, and then this will be our y direction. And then by the system of right hand rule, our z direction will be out of the page. So that is the right handed system we are following. And then in this system, T is the tension force is basically given by T, the magnitude, times minus x hat, which is this direction, and mg is given by mg cosine theta into x hat minus mg sine theta into y hat. So instead of r vector, we can write L times x hat crossed with f. Then in case of f, we have t plus mg. And then substituting for those, we have for t, we have minus t x hat. For mg, we have mg cosine theta x hat minus mg sine theta y hat. So clearly, x hat cross x hat is equal to 0, and x hat cross y hat gives us z hat. So in this case, we are going to have negative mdl sine theta z hat. So therefore, we get I theta double dot, which is ml squared theta double dot equal to negative mgl sine theta, which gives us theta double dot plus g divided by l sine theta equal to 0, which is our desired equation of motion. Now, if theta is small, if the maximum value of theta is small, then we can approximate sine theta by theta. Why? Because remember, if we Taylor expand the function of sine theta, we get theta minus 1 by 3 factorial theta cubed plus 1 over 5 factorial theta to the power 5 minus etc. etc. So these higher order terms all can be neglected with respect to theta if theta is too small. So then, if we do that, then the equation of motion becomes theta double dot plus g divided by L theta equal to 0. This is exactly like the simple harmonic motion or the equation for simple harmonic motion that we found earlier. And so therefore, by the equivalence of the form of the equations, we find the angular frequency is given by square root of d divided by L. Remember, this is the angular frequency. This is, first of all, a constant and a characteristic of the system. So, characteristic of the system. For most of the part, what is confusing to many people is that they equate it with the concept of angular velocity. And to complicate things further, the angular velocity also utilizes the same symbol omega. But this is purely a coincidence. The angular velocity and angular frequency are totally two different things. So omega has the unit of radian per second, the same as the angular velocity, but that's another coincidence. However, angular velocity and angular frequency, as I'm emphasizing again and again, are two different things. This is a constant, and angular velocity can be a constant or a variable. If it's a uniform circular motion, then angular velocity will be constant. But if it's not, for instance in this case, the angular velocity will be changing with time. So by the analogy, the solution to this differential equation, which is rewritten as theta double dot omega naught squared theta equal to 0, is given by theta, which is a function of t now, equal to an amplitude theta naught and then sine omega naught t plus delta. Now, in order to avoid confusions, we'll be calling this amplitude capital theta. And we notice if we differentiate it once, the angular velocity, by the way, which is again a function of time, is given by omega naught capital theta cosine of omega naught t plus delta. Notice this is the angular velocity, and this is the angular frequency. The angular velocity is not a constant. It is changing with time. But angular frequency is a constant. It's the characteristic of the system, and it is not changing with respect to time. And this discussion fulfills the 2 points in target that we had in our mind. The first one being the simple pendulum, the system of simple pendulum has a relation under certain conditions where it displays simple harmonic motion. And number 2, it clarifies the confusion between angular velocity and angular frequency. Before I finish this video, I'd like to emphasize on the fact that this is not the complete solution or the complete motion of simple pendulum. The actual motion is much more complicated than this. And the second one is that we'll be discussing the solution or the complete solution of simple pendulum in a separate video. But for now, in the context of oscillation, I think we have done our job. So as far as the topic of simple pendulum goes, we'll be stopping here, and we will come back to it after we are done with oscillation. If you have liked this video, please give it a thumbs up and subscribe to this channel. And happy learning physics. See you in the next video. Bye bye.